Hydrograph's calculations provide a method of evaluating an existing sprinkler system design with respect to an existing water supply. The calculations use the affinity formulas that provide the basis for the graph. Note that Hydrograph is not a hydraulics calculations program. It cannot compare designs of differing design areas, and it cannot compare a density area method design to a CMSA or ESFR design. With that said, let's get started. First, I will load in a file with a simple demand and supply already entered. The demand line was created from the entries in the demand dialog box. The plotted point is the design demand point of 0.19 gallons per minute per square foot. This generates a demand of 380 GPM at 58 psi. The supply was created from the entries in the supply dialog. This was a simple hydrant flow test flowing 800 gallons per minute at 30 psi. Right away, you can see that the sprinkler demand point is under the supply. So there's enough water to supply the demand if we ignore the hose stream demand. However, for insurance purposes, we generally like to be conservative and evaluate the protection of the total demand. To generate the total demand, we need to open the calculation dialog. The calculation dialog is broken into three areas: required design, density calculations, and density estimates. The entry in the required design section is simply the design you wish to evaluate. You can evaluate the placard design or a higher design if the fire load requires it. If you make no entry and press the calculate button, the program will evaluate the placard design. Density calculations will show the demand to provide the required design. 2 points are generated, one with hose demand included and one without. The density estimate box shows the expected performance of the system with the current water supply. Again, 2 points are shown, one with the hose allowance and one without the hose allowance. The without hose allowance is easy to visualize. It is the intersection of the supply and demand curves. The second point can be a little harder to understand. It is the supply available to the sprinkler system when the hose streams are subtracted from the supply. This will become clear when we hit the calculation button and look at the example. First, looking at the density calculations, you will see the required point is the placarded demand point. The calculations show the demand of 380 GPM requires 58 psi and has 75 psi available, leaving a safety factor of 17 psi. The second point in the density calculations is the total demand with the hose streams. So 250 GPM are added to the 380 GPM sprinkler demand, yielding a total demand of 630 GPM. This total demand needs 58 psi to provide the placard design. The calculations show we only have 51 psi available, yielding a negative safety factor. The density area, the density estimate area shows the performance point, the intersection of the two lines, is 431 GPM at 71 psi. This will give us a minimum density of 0.22 GPM per square foot, or about 116% of the required. However, looking at the total demand, we can see the sprinkler system will actually have only 361 GPM at 54 psi. This yields a density of 0.18 GPM, or about 95% of the placard design. I'm going to plot the two total demand points to help better explain what's going on here. The first point, the required point with hose, should be pretty obvious. It is simply the placarded point plus 250 GPM hose. The second point can be a bit confusing until you see it graphed, and the hose stream is graphed with it. Let me graph the hose stream, which would be 611 at 54. 611, 54, rectangle. And you'll see that the point falls exactly on the intersection of the demand plus hose and the supply line. The 361 GPM is what's available for the sprinkler system. As a last exercise, let's look at a new higher demand point, say 0.24 GPM per square foot. I don't need to do that. I need to go to calculations, 0.24, and calculate. You will note the density calculations change greatly. Hitting this new design requires a lot more than the supply can handle. The density estimates have stayed the same. The two lines still intersect at the same point. However, the percentages have changed as the program compares the delivered density to the new required density. That's about it for calculations. Oh, another question I get is, can I graph two different demands on a single graph? The answer is not easily. If you want to display a second demand line, you can add it with the line on the ribbon. However, if you want to perform calculations, you can't do it on this line. Entering in as a second demand will erase the first demand calculations. So the answer is, and I apologize for being so convoluted, is to create two graphs and overlay one graph on the other. Here's an example. As you can see, the graphs can get pretty messy and require some significant touch up. I'll overlay the second demand. So if you do it, expect to spend some time cleaning up the graph. That is the end of this presentation. Thank you.